Okay, good morning. This is ELEC 1013 network cabling, second week of our winter semester 2025, January 13th. So Friday the 13th, this month is on Monday. There we go. All right. Let me start right away with something here. I need to get some concept right away. Where is my board? Here is my board. There we go. All right. So here's the concept of, based on which we're going to conduct a large part of our class or lesson today. Let's say here is a let's say here is a piece of wire, and it's part of some kind of a circuit, so it's just a cutout of a already circuit that is conducting a current. And let's say the current I flows in a conventional way, which would be from the more positive to the less positive side of anything that's in the circuit. So that's a conventional current flow. Now, when we have current flowing, we do have electromagnetic field, and magnetic field is basically spinning around the wire in this way here. Okay. Now, if we place another wire close proximity to that wire, and let's say this magnetic field is strong enough that it actually embraces both of the wires, then the current is going to be induced by the means of the magnetic field induction. So the flowing current in the active wire is going to cause a current flow in the other passive wire. Providing that there is a change. Any kind of a change in magnetic field is going to be registered and is going to dissipate as current flow in the other wire. All right. So that's by the means of induction. Now, when you take that wire, and I'm just going to erase that. If you take that wire and if you, let's say, make a coil out of that. Oops. Where's my pen? Here. Make a coil out of that, just like that. All right, you wind it as a coil. All right. Then all those magnetic fields that are spinning around over here, they're going to kind of grow in force right here to the point that you're going to have one stream of magnetic field, because they're going to just add up. Now, if you put another coil beside that stream of magnetic field, that flux of magnetic field is going to cause a current flow in the other coil if you place it in close proximity. And sometimes the second coil is just wound right on top of the other one. Right? So that's what's happening. Now, when it comes to, this is just a quick review of the transformers. Transformers, power in the skies. There we go. My positronic brain is going to heat up, overheat, something like that. Positronic circuitry. Remember that? That was an old cartoon show. Okay, so if you have a transformer of primary, let's say this is the primary, primary winding, and let's say it has 100, maybe 10,000 wounds, right? Not 100, 10,000 wounds. And if you have another one that has only half of that, let's say 10,000, let's say this one has 5,000 wounds. So the ratio is 2 to 1. Okay. So the voltage, if you have the AC, it has to be AC. Well, it doesn't work on DC. Okay, it works on AC. Alternating current. If you let's say have 100 volts AC, And it could be RMS or peak to peak or whatever, just as long as you stick with the same units on the left side or right side against on the other side, then we're going to have the ratios going on. So let's say 100 volts AC on this one, ratio 2 to 1. So you're going to have across these two terminals, you're going to have, well, 50 volts AC. So the number of wounds, the ratio of the windings determines the ratio of the voltages. Now, here's the cool thing about the transformers. Whatever the power is flowing in that, whatever the power this circuit right here on the right, there could be some resistor going on, some power supply. There could be something going on as power being dissipated in this whole circuit. On the right here, which is the primary side of the transformer. Then the secondary winding is capable of having the same amount of power that's on the other one. So the transformers, they transform some things, but they transfer others. One thing is that it flows through, whatever is kept from one to the other is power. Right. Now, what's the formula for the power? Power, if it comes to RMS, equals current times voltage. Just look, over here we have the ratio of the windings. Here's 100 wounds, 10,000 wounds, and over here is only 5,000 wounds, which means the ratio of the windings is 2 to 1, which means the ratio of the voltages is going to be 2 to 1. So we have certain power, the power here is same as power here, so the voltage here has gone down on this one here. In order to keep the same current, the same power, then the current in the circuitry here will have to go up in order to preserve that equality sign. The power of the primary is equal to the power of the secondary. So the transformers transfer power, they transform voltage, and they transform current. They also transform Z. Who is Z, baby? Z is dead. Z thing stands for impedance. Impedance. I'm just writing with my mouse. All right, so transformers transform current, they transform voltage, and they transform impedance. They keep or transfer the power. All right. So that's what we're going to have to deal with right now when we're talking about something that's called the distributed audio. Okay. Just going to minimize that, and I'm going to start this presentation right here. Let's see if we get the proper screen in the proper place. Yes, we do. All right. Slide number 1, PA system. PA stands for public address. And we already know that, that car. Here's an example of a public address system. It has some sort of processing unit. It does have that. Oh, well. It does have that here. You can see the basic model of a transmission system. All right. So on here, we do have a simple processing unit that has a transducer as a microphone and some kind of a processing unit that pre-amplifies the signal from the microphone and then processes that and amplifies that into a bunch of horns. Horns versus loudspeakers. They behave a little bit different. They work the same way. However, horns are designed, just as a side note, they're designed for mid and high ranges. So for spoken word, announcements, and things like that, they cut through any kind of production hall noise quite well. They cut through that. Or if you have any football game outside, if you have a bunch of horns, they will do a really good job. Because the other thing, the further away you stand from the horn, the better it sounds. And it's not really designed for playing music. You can pump some music through it, just so you could say you did that. But it's not designed for high quality, hi-fi, high fidelity music. It's meant for mid-high, which is human voice, mid-high range. Okay. Now over here's more of a full spectrum. Here we have a subwoofer and we have a bunch of tweeters and all that stuff to accomplish a full range sound system. So there are different PA systems are going to be used for different applications. Okay. Public address system. All right. Description. It's an audio system consisting of audio sources, amplification equipment, and output transducers, also input transducers, right? Such as a loudspeaker. Yep. Now here, purpose of that is to process, amplify, and distribute audio signals over a large area. Well, we get the definitions out of the way. Well, not yet. Essential parts, we remember that from our last class. Example of input transducers would be a microphone, MP3 player, or a CD player, or any kind of a output from a radio, or no, I don't want to use the word tape deck, but that's what comes to my mind. And guitar, from the guitar pickups. Now, for the transmitters, with preamplifier, mixing console, and maybe a telephone system. But the telephone system could be also included in the input part right now. So it depends on how you connect things. Of course, for the links between the parts, we have copper cables, we have fiber optics, and we do have wireless links. And the wireless, or anything of those, they could convey, any of those mediums, they could convey signal in digital form or an analog form. Receiver, in this case, we're going to have an audio amplifier, and the output transducers would be loudspeakers. All right. We have that already, remember that one. Okay, definitions. Now, when working in the field, you're going to have to deal with a bunch of definitions, and depending on the company that you work for, or maybe you're collaborating and working together with other companies on certain projects or whatnot, you're going to have to establish some common definitions, because what something means to one company and people understand by saying something, they can understand something, and the same word can mean something else in different environment. So when you're dealing with contracts, make sure you got the definitions down pat, that you have to that you have all basically the same understanding about the terminology that you use. So, as what I said here, in written installation contracts, the language might differ. Always confirm the definitions for every contract. For example, the sound system used to amplify rock concerts is commonly called as the PA system, or just simply PA, while technically it's a sound reinforcement. All right, so just make sure that whenever you're dealing with contracts, that you establish some of the definitions. Here's some to help you with. Sound reinforcement: any system which amplifies one or more sound sources for a live audience. Now, here is a public address PA system: public announcements and background music. Sound reinforcement. Well, the background music also could be as a foreground music if you're dealing with a concert. If music is the main thing. All right. So sound enhancement. So here's a public address, sound reinforcement, that's everything is included in the sound reinforcement. Now we get the public address, now we have sound enhancements. Sound enhancements is used mostly in the meeting rooms or conference environment. We can deal with some of that. Maybe I'll show you what I mean. And also here's something that's called a hearing impaired. Let me just give you some idea of, for example, this one here, we know what it is, more or less, be a stage, theater, hallway in a school or a hospital, things like that, or a production hall. So depending on the purpose, you're going to install this the sound system a little bit different in a different way. Now let's say let's take a look a little bit at the sound enhancement. All right, where's my board? We'll come back to that transformer thing, I promise you. Okay, let's say we have a room. We have a room. Here is our room. Here is maybe some press conference or whatever it is. Here's the table where the people sit here and they talk, and or maybe there's some speaker that talks to an audience. And over here we have seats. I'm just going to draw them just like that. Here's the audience. Let's say the room is long enough that the sound needs a little bit processing in order to convey things properly. It is understood that the sound, more or less, the speed of sound is about 1,000 feet per second. Now, if we have something like from here to here, if we have something like 100 feet, and that's not that far, not that difficult to accomplish, then here's something that's going to happen. Let's say this is a big meeting and we need to have some sort of help with the sound in order to convey things properly to the audience. So let's say we're going to run a bunch of microphones, or one microphone or a cluster of a microphone, let's say overhead, above, in the ceiling, just pointing at this area here. And over here, let's say we're going to have speakers. Here's one row of speakers, here's another row of speakers, here's another row of speakers. So here's what's going to happen. If you have an amplifier over here, and all these microphones are connected to this mixing board and connected to an amplifier, and this one here, it's just the amplifiers just provides the connection to the speakers. So here's what's going to happen. Because the sound is traveling 1,000 feet per second, if you have a microphone close to this person's source of sound, which is the person's mouth, that sound is going to have enough power for the person to hear in the last row, but it is going to travel at 1,000 feet per second. It is going to take very, very short time, but still is going to take some time to travel to that person's ear. But what's going to happen, if you have the amplification system, electronically, you are almost going to hear it right away in the speaker. So what is going to happen? You're going to have pretty much right away the sound hitting person's ear from the speaker, and slightly later you're going to have the sound from that person's mouth. It is going to be a very annoying effect. So what's going to happen, what you need to do is you're going to put this line of speakers on one of the channels of one of the amplifiers. You're going to take another line of speakers and you're going to put it on another channel of another amplifier, and you're going to take those and put into another channel of another amplifier. From the mixing board or from the processing unit, you're going to have delays. So this right here, this line of speakers is going to have the most delayed sound, not so much delayed sound, and maybe none, if any, over here. In that way, you're going to time align that the sound. So this here line of speakers, they're going to wait for the sounds to get from that person's mouth to this person's ear, and if you delay that just the right amount, you're going to have them hit at the same time, and it just makes a day and night difference when it comes to the receivage of the sound. So that's basically how the conferencing systems are being done. Now, a well put together and well adjusted conferencing system works in a way that the audience the people don't even realize that there's a sound system there. Because you don't need to know. The main objective of this whole thing is that there's a comfortable way of conveying sound or hearing and comfortable communication. So the person, anybody here will have not the illusion, but they will be under the impression that they hear the sound from that person's mouth. This way, the conversation is comfortable, no distractions and whatnot. The only way to know, for people to notice that there is a sound system there, is that if somebody pulls the plug on that and things are just getting a little bit more quiet. Right? So that's a properly set up conferencing system. Okay, so here's meeting rooms and conferencing environment. Hearing impaired audio enhancement is for people with challenges that maybe they're hard of hearing. Right? Usually there will be the older audience, and this is a extremely popular system in the church systems. It is if you are in the church audio systems installations, then you're going to have a hard time selling that, because people don't want to admit that they are hard of hearing, especially men. They don't want to admit. I'm talking from experience, and there are millions of articles written about that. Okay? It's just the way it is. But once you give here's the thing. Once you give someone to try it, then they're sold. They don't care about admitting or not admitting. They just are happy that they can hear things properly. Right? So, all right. So that's as far as the classifications of sound systems, sound reinforcement, sound enhancements, public address systems. All right. Remember the transformer thing? Here is where it comes to play. Before I do this, I'm going to give you another scenario here. Let me erase this. Let's say, all right, we probably know the Ohm's law, or, well, it's derived from Ohm's law. But how is it that we add resistances? If we have a resistor, and we have another resistor, and we connect them all together. So there's R1, R2, R3. And we connect those, and we have a couple of terminals here. Across these terminals, the total resistance is it is equal to R1 plus R2 plus R3. Okay, now if we have another scenario, if we have the resistors like this here, here's R1, R2, R3, and if we connect them in parallel, and here's our terminals, Then here's the thing. 1 over R total equals to 1 over R1 plus 1 over R2 plus 1 over R3. So here's the basic formulas as far as the adding resistances in parallel or in series. Okay. Well, let's see here what we have to deal with when it comes to commercially installed PA systems. The amplifier. Okay. The output impedance usually is 8 ohms. Which means when it comes to supplying the load, let's say total kind of a load, it has to be 8 ohms. And we can talk about that later. I'm not going to give you a lesson on that because you're going to get this type of stuff in other subjects. And you're going to get a repeated lesson like that in other subjects. The main idea is that the impedance, and what's impedance? We'll talk about that later as well. Impedance is a combination of resistance and something that is called reactive resistance or reactance. And when it comes to resistor has is a passive linear piece of equipment, and its resistance remains constant whether you run DC, high frequency AC, low frequency AC, whatever you run through it, it is going to have 8 ohms resistance if that's an 8 ohm resistor. If it's a coil, then its resistance is going to depend on what frequency you're going to apply to it. It is going to resist certain frequencies more, and it's going to resist certain frequencies less. It reacts to what kind of frequency you run through it, which was called reactive resistance, reactance. And you combine these two because every element is made out of, every part is made out of physical things because we live in a physical world. Everything is going to have a little bit of resistance. It's going to have a little bit of reactance, except here's the thing. Resistance will have a little bit of inductance naturally occurring, but it's going to be so insignificantly small that we can ignore it. A coil, if it says we have a coil, the main quantity of the characteristic of the coil is its inductance, and it also has a reactance. Okay, so the XL, inductive reactance, it is going to have reactance as the main thing of its characteristic. Yes, it's going to have little tiny bit of a resistance, but it's going to be so insignificantly small that we can ignore it. All right, let's not get too complex with things. All right, why do we need the output impedance to be the same, or the load, impedance of the load? Why do we need this thing to be matched with the output impedance of the amplifier in our case? As I said, 8 ohms is the most common impedance that's on the output of an audio amplifier. There are also amplifiers that are designed for 4 ohms, even as low as 2 ohms, that's whoa. Or some of them are 45 ohms and so on. But let's say we're dealing with 8. Why do we need these to be matched? The idea is, can we get some, come on, give me some colors here. There we go. get some text here. And I can't change the colors. What's going on? Here is my color. Can I type? There we go. For the idea that is called a maximum power transfer. That's the idea. In order to achieve a maximum power transfer from the output of the amplifier to the load, we need to match the impedances. If the impedances, just so you know now, if the impedances are mismatched, then you're not going to achieve a maximum power transfer. And depending on which is different in which kind of way, some of the power might get into the cable and it's going to dissipate as heat. They're going to have a loss. Or what's even worse, some of the power can dissipate as power inside the amplifier. It's going to get lost as it's going to manifest itself as a heat loss. So it's going to heat up the amplifier. That's why. When we have, let's say, here is the stage. That's when it comes to, let's say, theater, church, rock and roll stage, or whatnot. Here is something that's called front of the house, FOH. That's where the audience is. And that's usually where the strategic point is going to be a mixing board. And let's say there is 150 feet between those. You want to have all the processing equipment here, but you want to have, because that's where the speakers are. Here are going to be lots of speakers, maybe a center cluster or something like that. You don't want the amplifier to be here. You don't want the amplifier to be here. You want the amplifier to be somewhere close to the speakers, because 8 ohms, or when it comes to staging like that, you're going to have maybe even 4 ohms, or maybe 2 ohms as far as speakers. Then the resistance of the wire would be comparable to the impedance of the speakers, and some of that power is going to be just lost in the cable. So you want the cable between the output of the amplifier and the speaker the shortest distance that you can have. All right, so we have gone through the adding resistors. All right, let's say you have four speakers or 6 speakers. Let's see. Let's say you have 4 speakers. Here's a speaker, here's a speaker, here's a speaker, and here's a speaker. All right. Now, when we add, because they're all, let's say they're all 8 ohms. Now, as far as impedance is not to be measured with an ohm meter of your multimeter. However, when it comes to audio speakers, their impedance is really close to their resistance. So, yeah, you can sort of measure the impedance with the multimeter. But it's a very specific case. Just, because when you're going to see me or somebody else measuring the impedance of the speaker with a multimeter, and you're going to have something close to 8 ohms, because it just so happens that in audio speaker, those are close. But it's not to be understood that you can measure the impedance of any kind of coil with a multimeter and say, okay, that's the impedance, because you're going to get a false reading. But let's say right now we have that case. If we have these 2 speakers here, for example, if they both are 8 ohms, if you connect them in series, you're going to have 16 ohms. If you connect these two in parallel, you're going to have 1 over the total resistance equals 1 over plus 1 and 1 over that. And it just like, if they are equal, there's a trick, there's a shortcut you can take. If they are equal impedances, it's very easy to calculate. You just take the impedance of the speakers and divide that by the number of the devices. The math just works out that way. So if this is 8 ohms and this is 8 ohms, you connect them in parallel, divided by how many of them you have? 2. So 8 by 2 is going to have 4 ohms. So let's say you're going to connect these two. How do I do it in parallel here? If you connect, let's just have them drawn like this. I'm going to draw it like this here. If you connect these two in parallel, parallel here, just like that. And if you connect these two in series, you're going to have, no, actually here, no. You also connect these two in parallel. So I'm going to draw them like this. Bear with me. Gonna have the same thing here. Oops. Come on. Connect these two. Some of you already know what I'm getting at here. These two already also are going to be connected in parallel. So 8 ohms connected in parallel, this is going to give us 4. Same thing, we get 4. Then we connect these two in series. We're going to add 4 and 4. We're going to end up with 8 ohms, which is what the amplifier wants to see. So that's called series parallel combination. You can do that. Okay, here's 4 speakers. Well, here's where the problem is. Let's say you have a whole school to connect. And you have a hallway. You have another hallway. And you have another hallway. And this hallway is going to have maybe 30 speakers. This one another going to 25 speakers. And let's say this one is another 30 speakers. 30, 60, 70. You got 85 speakers altogether. The amplifier wants to see 8 ohms. Each speaker is 8 ohm. Can you connect all those speakers in? You have to draw it out, and you have to do series parallel. You can do a little bit of a spider work, and you can accomplish 8 ohms here out of all those by doing that trick with series parallel combination. Problem with that is that it's not very practical, because it's very easy to make a mistake. It will take too long. And what if you need to add one more speaker somewhere? The whole thing just goes to toilet, just goes to the garbage. You have to disconnect everything and connect it. So here is something that we have established that is called a constant voltage distributed system. Here's a signal coming from the amplifier. Here's the transformer. Here's a bunch of speakers and a bunch of transformers. Look, they're all connected in parallel. All right. Distributed system. Constant voltage. Why is it called constant voltage? It's because, look, this voltage same as this voltage. It's a wire. It's just basically in a bus configuration. So the voltage is going to be constant across the whole system. Now, what we have here is something that's called a step-up transformer. And it transforms from low impedance, because 8 ohms is considered to be low impedance, comparing to the high impedance. So there is not too many wounds, a lot of wounds here. We're going to have high impedance here. So here will be about 8 ohms, and here will be maybe a 1200 ohms or something like that, in the range of 1200, 1500 ohms, something like that. So it is a step-up transformer because it steps up the impedance. All right. Now, over here, we're going to have something that's called a step-down transformer that is going to be connected to every single speaker that you're going to install. This transformer will be relatively bigger than this transformer. This one is like, you have to maybe sometimes use both hands to lift it because they're heavy. And this one here, you can just close it with the palm of your hand. Step-down transformer. On this side, it has the high impedance to match the high impedance that is being shot out of that transformer. And it transforms to the low impedance because the speaker wants to see 8 ohms. And if you do that, you do not have to have the series parallel combination. You can just keep adding speakers. So you're going to pull a long, long line along the whole hallway. You're going to interrupt the wire, put in a speaker, interrupt the wire, put in a speaker station, and so on. And the beauty of that is that whatever the power consumption you set this, because there's power, so-called power taps. The transformers, this one here, these 2 wires are connected permanently to the speaker. Over here you have many wires. We go. So we have many wires, and for example, here's something that's called 70-volt line. There are, in the industry, 2 types of voltages, the constant voltages are being used. 70 volts or 25 volts, AC RMS. So if it's a 70-volt line, the amplifier has a 70-volt output, and that's where you connect the main line. And depending on which, it's going to be on the other side of the transformer, which is on this primary side of the transformer, which is connecting to the main line. The other 2 wires are connected to the speaker. We forget about that. They're connected there. They're connected. Over here, you're going to use the black common. Is there here black? Here says black common. So you're going to use one of those, the black, and the other one you're going to, depending on how strong that speaker station you want to be. Do you want to tap it at 1 watt? Because 1.25 is considered 1 watt. 1 watt or 2 watts or 5 watts or 10 watts, which means if you use the yellow, black, and the yellow only, and the other ones are going to be disconnected, well, not connected actually, then the transformer, the speaker station, is going to use 1.25 watts at the full volume setting of the amplifier, and so on. So you get the taps. Now, let's say you set all the speakers at 1 watt. All these 2, you choose the black, which is common, and in that, because different companies, they produce different transformers in a different way. Some of them have different colors, but they put that little legend, they put that little sticker on the transformer to see what's what, for you to see what's what. Some of them don't have wires, some they just have spade taps, and you can just connect that. Every transformer looks different, but it's the same idea how it works. And if you connect the black common to the yellow, which is going to be 1 watt, and if you have an amplifier that is capable of outputting 100 watts, And if you tap each one of those at 1 watt, then you can use 100 speakers tapped at 1 watt. That's how simple it is to calculate the power, how many speakers you can put on one channel. If you tap those at 2 watts each, which means at the full volume, that station is going to grab 2 watts. Then you can connect only 50 of those. Simple, right? This is basically how things look like on the other side of the amplifier. Here's the common. Now, some of the PA system, the commercial PA system amplifiers, they have that transformer built in, the big one. And over here you have different outputs. So if you have 4 ohm speakers, you connect it, if you have 8 ohm speakers, See, there's one 16 ohms, and here's a 70 volt output. So you're going to one wire here, one wire here is your main line. That line here is connected to this. Here. This is what the typical speaker station looks like. Here's the speaker baffle. Some of them are round, some of them are square, depending on the situation. And here's the step-down transformer right there. Here's a volume control. The volume control also is just not like a slider or just a sliding action. It is actually a transformer, but instead of tapping into the wires connecting, there's a switch that taps into the. I'll show you how that works later on, because we're running out of time here. And here's a paging horn. At the other side of that, it just has 2 connections, and there's like a screw terminal. So with a slotted screwdriver, you just tap into which wattage you want to set that to. That's what the transformer looks like. We just talked about that. And let's see, remember that one we talked about last time? Here's the crying room for the church, for example. Here's a 70 volt amp. Here's the volume controls. Here are the speakers in the crying room. You can when you can run the wire to the volume control first, and then from the volume control to the speaker, then you're going to control the volume on only that speaker. And if you control that, nothing else is going to get affected. All right. That's the first lesson of the distributed audio system, and the next lab after this, after the deliverables, we are going to we're going to connect just that, the bunch of speakers like that, and we're going to play some music through them. So we're going to have some fun connecting the constant voltage distributed audio system in the lab, but now you have some sort of theoretical background on what actually you're doing and why this thing is being done. All right, so this was the first part of the PA systems lessons, and the second part we're going to have a little bit more practical applications with some of the staging gear and stuff like that. All right, so that's it for today, and I'll see you when I see you. Thank you so much for your attention.